What if I told you there's an 80-year-old algorithm setting the price of your next plane ticket, routing your FedEx package, deciding which power plant turns on at the exact moment you flip a light switch? And it was invented by a 26-year-old Soviet mathematician asked to cut plywood more efficiently. Now, his paper sat mostly ignored for decades. Today, it steers over $10 trillion in decisions a year. Almost no one outside operations research knows his name. This is linear programming. Leningrad, 1939. Leonid Katarovich is 26 years old, a mathematics prodigy who entered Leningrad State University at 14 and began research while still in his teens. He's been invited to consult for a plywood trust. The problem seems mundane. The factory has different machines, each capable of cutting plywood sheets in different patterns. Each pattern produces different quantities of different products. The question: which machines should run which patterns and for how long to maximize total output? Kantorovich tries the standard approaches. None of them work efficiently. So he invents something new, a method for optimizing a linear objective subject to linear constraints. He calls it the method of resolving multipliers. He publishes it that same year. The work has limited immediate impact. Kantorovich's math implied that resources carry implicit prices determined by scarcity, which sat uncomfortably with a central planning system that set prices administratively. His paper remained largely unknown outside the Soviet Union for years. Meanwhile, 8 years later and half a world away, George Danzig is working for the United States Air Force. It's 1947, and the military needs to coordinate training schedules, supply logistics, and troop deployment at massive scale. Danzig develops what he calls the Simplex Method, a systematic algorithm for solving exactly the kind of problem Kantorovich had described. And there's a wonderful footnote to the story. As a graduate student at Berkeley, Danzig arrived late to his statistics class. He copied down 2 problems from the blackboard, assuming they were the homework. He solved them and turned them in a few days later. They were actually 2 famous unsolved problems in mathematical statistics. He didn't know they were supposed to be impossible. That's the kind of mind that built the Simplex Method. 2 mathematicians on opposite sides of the Cold War, independently discovering the same fundamental idea. One remained little known outside the Soviet Union for years. The other turned the idea into the method that carried it into the modern world. Every optimization problem, every single one, has exactly 3 ingredients. And once you see the patterns, you start noticing it everywhere. First, an objective function, the thing you're trying to maximize or minimize. Profit, cost, distance, time, it's the scoreboard. Second, decision variables, the knobs you get to turn. How much of each product to make, which route to drive, how many hours to allocate to each task. Third, constraints, the rules you cannot break, your budget, the hours in a day, the capacity of a warehouse, a regulation that says a thing must happen within a specific window. Here's a concrete example. You're a farmer with 100 acres and 12,000 gallons of water for the growing season. You can plant wheat or corn. Wheat earns $200 per acre and needs 80 gallons of water per acre. Corn earns $300 per acre but drinks 200 gallons. The objective? Maximize total profit. The decision variables: how many acres of wheat and how many acres of corn. The constraints: land can't exceed 100 acres, water can't exceed 12,000 gallons, and you can't plant negative acres. Written as math, it looks like this. Maximize 200x plus 300y, subject to x plus y less than or equal to 100. 80x plus 200y less than or equal to 12,000, x greater than or equal to 0, y greater than or equal to 0. That's a linear program. Linear because every term is just a variable multiplied by a constant. No squares, no exponents, no variables multiplied together. Straight lines all the way down. Now here's where linear programming gets beautiful. Take those constraints and draw them on a graph. X on one axis, Y on the other. Each constraint is a straight line. The land constraint, X plus Y equals 100. draws a diagonal from the point 100, 0 to 0, 100. The water constraint, 80x plus 200y equals 12,000, draws another line. And the non-negativity constraints keep us in the first quadrant, the upper right portion of the graph, where both values are positive. Now look at what these lines create. They carve out a shape, a polygon. Every single point inside that polygon satisfies every constraint simultaneously. Mathematicians call this the feasible region. It's the universe of all legal answers. Any point inside is a valid farm plan. Any point outside breaks at least one rule. In our farmer's problem, it's a quadrilateral with 4 corners, and every point inside represents a different split between wheat and corn that actually works. But here's the insight that makes everything click. The fact that makes linear programming computationally tractable. For a bounded linear program, there's always at least one optimal vertex, a corner of the polygon. Sometimes the optimum is unique at a single corner. Sometimes an entire edge or face is tied for best, but you never have to search the interior. The corners are always enough. Why? Think about the objective function 200x plus 300y as a family of parallel lines on the same graph. 200x plus 300y equals 10,000 is one line, equals 20,000 is another, parallel and further out. As you increase the profit target, the line slides across the graph like a ruler. The last place that still touches the feasible region as you push it to the absolute limit is a corner. Or in a tie, the edge connecting 2 corners. It's like pushing a straight edge across a cut diamond. It comes to rest at a vertex, and this generalizes 3 decision variables. The constraints form planes, and the feasible region is a 3-dimensional polyhedron, a shape with flat faces, straight edges, and sharp corners. 1,000 variables? The feasible region is a polytope in 1,000-dimensional space, but the fundamental truth still holds. An optimal vertex always exists. So the optimal answer is at a corner. Great. But how do you find the right corner without checking all of them? Because in realistic problems, there can be more corners than atoms in the observable universe. That's where the Simplex Method comes in. Think of the feasible region as a crystal, a many-faceted gem floating in mathematical space. The Simplex Method is a marble rolling along its edges, always moving uphill toward better solutions. Intuitively, Simplex moves from one improving corner to another. Start at a vertex. The origin, 0 wheat, 0 corn, 0 profit, is an easy choice. Look along each edge, leaving that vertex. If moving along an edge would increase the objective, take it to the next corner. Repeat. The algorithm terminates when no edge leads to a better neighboring vertex, and the deeper reason this works is convexity. A linear objective over a convex feasible region doesn't hide better pockets off in the interior somewhere. If you can't improve by stepping to an adjacent corner, there's nothing better anywhere. For our farmer, start at 0, 0. No crops, 0 profit. Move along the x-axis to 100, 0. All wheat, $20,000. Then move to the neighbor where the land and water constraints intersect. About 66 2/3 acres of wheat, 33 1/3 acres of corn, for roughly $23,333. Better. Check the remaining neighbors. None improve it. Done. The elegance is in what the Simplex Method doesn't do. It never explores the interior. It never samples random points. It only touches vertices, and it only moves to better vertices. In 2 dimensions with 4 vertices, this is trivial. But in real applications, 10,000 variables, 50,000 constraints, the polytope might have more vertices than particles in the universe. The Simplex Method doesn't care. It just needs a short path from start to finish. And in practice, the number of steps is almost always roughly proportional to the number of constraints, not the number of vertices. It's one of the great empirical mysteries of mathematics. But almost always, fast isn't the same as always fast. In 1972, Victor Klee and George Minty constructed a worst-case polytope, now called the Klee-Minty cube, where the Simplex Method visits every single vertex before finding the optimum, exponentially many steps for a problem that looks simple on paper. This was a theoretical embarrassment. Linear programming was being used to solve enormous real-world problems, but nobody could prove it was fundamentally efficient. Then, in 1979, Leonid Khachiyan proved something remarkable. He showed that linear programming can be solved in polynomial time, meaning the computation grows manageably as problems get bigger, not explosively. His ellipsoid method works by enclosing the entire feasible region in an ellipsoid, then shrinking that ellipsoid by a guaranteed factor at every iteration, zeroing in on the optimum. Polynomial time, guaranteed. The ellipsoid method proved LP was efficient in theory. In practice, though, it was actually slower than the simplex method it was supposed to improve on. In 1984, Narendra Karmarkar at Bell Labs introduced a new interior point method. Unlike simplex, which walks along edges, interior point methods cut straight through the middle of the feasible region, and modern versions use barrier functions, mathematical guardrails that keep the path away from the walls while converging on the optimum from the inside. Today, mature LP solvers, Gurobi, Simplex, the open source hikes, use both families of techniques in combination. They can solve problems with millions of variables and millions of constraints in seconds. The total speed up since Danzig's 1947 simplex method is enormous, thanks to decades of algorithmic advances on top of steadily faster hardware. So where does linear programming actually run? The short answer is, everywhere you can't afford to be wrong. Airlines helped pioneer this world. American Airlines in the 1980s built one of the canonical early revenue management systems, combining demand forecasting with optimization to decide which seats to sell at which prices, how to assign crews to flights, and how to overbook without stranding passengers. Published estimates from that era credited revenue management with hundreds of millions of dollars a year of additional revenue for a single major carrier. UPS built a system called Orion, on-road integrated optimization and navigation. It optimizes more than 55,000 delivery routes every day, and UPS publicly projected $300 to $400 million per year in savings when Orion was fully deployed, largely by shaving a few minutes off each route. The California Independent System Operator, the organization that runs most of California's electrical grid, serving roughly 30 million people, runs a security-constrained economic dispatch optimization every 5 minutes. Every 5 minutes, it decides which power plants to run, how much to generate, and how to route electricity through the transmission network without overloading a single line. Google's ad system, the thing that decides which ads you see when you search and what advertisers pay, is built on auction theory layered on top of constraint optimization. Bids, ad quality, thresholds, search context, and the expected impact of ad assets all feed into that machinery. Enormous numbers of real-time decisions every day. And it doesn't stop there. The NFL schedule is a famous large-scale mixed integer optimization problem. 272 regular season games across 18 weeks, balancing broadcast slots, travel distance, stadium availability, and bye-week fairness. Modern supply chains, hospital staffing, portfolio optimization, finance, telecom network design, even cutting fabric in garment factories. Linear programming and its close cousins sit under all of it. Every linear programming has a twin. Mathematicians call it the dual. If your original problem, the primal, asks what the maximum profit given your limited resources, then the dual asks the mirror image question. What's the minimum total value you would assign to those resources that justifies not producing anything at all? That sounds abstract. Let me make it concrete. Go back to our farmer. The primal says maximize profit by choosing how much wheat and corn to plant. The dual asks, if you were going to sell your farmland and water to someone else instead of farming it yourself, what's the minimum you would charge per acre and per gallon that would make you at least as well off? And here's the beautiful part. The strong duality theorem says that when a linear program has a finite optimum, the primal and dual optimum values are equal. Maximum profit equals minimum resource value. The dual variables are called shadow prices. They tell you the marginal value of each constraint. For our farmer, solving this dual gives a shadow price of about $133 per acre on land and about 83 cents per gallon on water. Both positive, meaning both resources are scarce at the optimum. One additional acre of land would raise optimal profit by roughly $133. One additional gallon of water would raise it by roughly 83 cents. If a shadow price instead came out to zero for some resource, it would mean you had slack. More of it won't help. This is how airlines decide whether to buy another plane, how hospitals decide whether to add a nursing shift, how factories decide whether to invest in additional capacity. The shadow price tells you exactly what each binding constraint is costing you, and therefore what's it's worth to relax it. In 1975, Leonid Keterovich shared the Nobel Prize in economics for contributions to the theory of optimal resource allocation. The same ideas that had limited immediate impact in 1930s Leningrad had become part of the mathematical backbone of modern operations research. Today, linear programming is invisible infrastructure. It runs behind the scenes in industries worth trillions of dollars. It's not glamorous. There's no app for it. Nobody posts about it online, but it's there. Every time a plane pushes back from the gate on schedule, every time a package arrives by the promised date, every time the lights stay on and the grid doesn't buckle, the next time you book a flight and the price seems oddly specific, $47 cheaper on a Tuesday afternoon, that's not a coincidence. An optimization system found that price. The next time a delivery arrives faster than you expected, that's not luck either. An algorithm that started in a Soviet plywood factory now quietly optimizes the world. And you want to know what the remarkable thing is? The thing that still gets me is that underneath all of it is just straight lines. If this was helpful, don't forget to hit the like button and subscribe if you want to see more videos like this. Thank you guys for watching.